Okay, so let's start. So good evening or good afternoon or good morning, depending on where you are. My name's Simon Prickett. I am it's the second time talking at Raspberry Pi. The first time was with this thing that you see behind me, which is a very large flip dot destination sign from a bus that I had a project to control that and show different things on it. So we had a look at how all of that stuff worked. This time I am going to talk a little bit about a database project that I'm involved in and how it relates to Raspberry Pi and quite specifically to the Pico, because I also wrote the MicroPython client for this. So, really good way of getting going with the Pico is MicroPython. Stuart's going to tell us a lot more about the Pico afterwards. So I'm going to talk a little bit about how the MicroPython client I built worked, and also how you can distribute a MicroPython library yourself if you want to. So there's a few steps involved with that. So let's change that. So who am I? Like I said, I'm Simon. I'm in Nottingham in England. I always do a thing of declare your biases. So I'm going to be talking about CrateDB today, which is an open source database. So there's nothing to buy here if you don't want to. You can download it and run it yourself. It runs really nicely on Pi 4s and Pi 3s and Pi 5s. And it also comes in the cloud. It's my day job. So I am paid to talk about CrateDB. So with that out of the way, let's go along and see what we're going to do. So CrateDB is actually quite a fun database to use for hobby projects. So if you're building something with a time series and sensors and you're using Influx, you might want to consider using it. If you're building something with vector similarity and, for example, you're feeding a LLM or building a chatbot or something, you might want to use it for that because it stores all of these different things. So we'll quickly take a look at theoretically what is CrateDB. And the best way of looking at things is by doing. So we'll then move on and have a look at some regular Python stuff using data from the city of Chicago, just so we can get a feel for like the breadth of what you can store in there and the sort of queries you can make. And then this is obviously a Raspberry Pi meetup. It's Raspberry Pi stuff is a bit of my job and a lot of my hobbies. Everything you see behind me there, except for Domo Kun there, can run MicroPython, and it's all Raspberry Pi stuff underneath it. Most of the things back there are Pico Ws in various different forms. The bus sign's got a Pi 3 in it, and it's due an upgrade for a Pi 5 at some point. So we're going to look at how to collect sensor data with MicroPython and look at why putting it in CrateDB might be a good idea. And then more generally, I was going to talk about, okay, I'm the author of a MicroPython package. How do we get that distributed? And just quickly run you through some other example projects. And then we'll hand over to Stuart to learn a lot more about the Pico itself. So here we go. So very, very quickly, as I said, CrateDB is an open source database. It aims to be used for analytics and search. It also plays nicely with AI. And why would you be interested in this if you're interested in Raspberry Pi stuff? Well, quite often you are working with things that are an endless stream of data. So you might have like temperature and humidity readings that just, sensor pings those in forever. You might have some sort of event-based thing. You might be counting people going past a camera, or you might be counting cars in a road or anything like that. The thing with large streams of data is the value of individual bits of the data is very, very low, right? So one observation of I don't know, the temperature for something where you're recording it every 30 seconds or something because it's an industrial process, or you've got some sort of legal requirement to do it. One value isn't actually really that important, but what's important is the trends and aggregations and things you can do with a lot of those values. So an analytics database is great for that sort of thing. What can you put in there? So it's a database, you can put stuff in there. Usually databases specialize into one specific thing. So, it might be a time series database or a vector database or a document database. CrateDB aims to be a sort of broad store for all of the different data types. So we'll look at what that actually means. Um, Data in Crate is stored in tables. So it looks like a relational database.
Bladder issue. Well, like I said, and I do have some in
Hello,
contents,
we got
but
somebody in the background.
when I'm home, when I visit work inside my hours, but I try to get what I
Thanks, Richard. So data lives in tables. The tables have flexible schemas. So if you're familiar with working with a table relational database, a lot of your life is altering tables, doing migrations, messing around with the schema. In CrateDB, those can evolve dynamically, and we'll look at what that means with some picos. And everything is indexed. So again, with analytics databases, when you put data in there, you don't necessarily know what analysts are going to do with it, what sort of queries they're going to make. So we take an approach of indexing everything so that ad hoc queries should be fast. They should always hit an index. Uh, is it something that is sort of way out there in left field and I have to learn a whole new stack for? Well, no, because it has a SQL query interface. So if you know SQL from another database, say Postgres or MySQL or Oracle or whatever you've been using, you can bring that knowledge across and use it. Similarly with your drivers, so it talks Postgres. So anything that you can write with a Postgres driver, or if you're used to using tools such as Grafana that connect to Postgres and visualize like all of your sensor data and things once you pull them into a database, you can use those. So moving along, what are we trying to solve with this database? Generally, we're trying to solve for a problem where there's loads and loads of different types of databases that all have their own little sort of fiefdoms or niches. So you might have decided you want to do some sort of full text search over your data. So you might go get like a Elasticsearch or an OpenSearch type product. You might have random JSON data, which is also fairly common with dealing with small devices, IoT, and the Raspberry Pi things. So you might have picked a database like Mongo for that. Another common thing with little devices and something I love working with is geospatial data because things move around a lot. You can plot it on a map. That's kind of visually interesting and it's a fun way of getting into things. So there are databases for all of those things. And then you may well be fairly familiar with time series databases such as say Influx or Timescale, because if you've been working with little devices, quite often you are just sending in a time stamped signal or sensor value, and then using one of these databases to make sense of them. So generally, if you start building complicated things, you end up with lots of these needs. And what we aim to do with CrateDB is have a single place that you put all of these things into. So everything lives in a table, looks like a relational database. However, inside the table, columns can be time series data or JSON document data. They can be full text index. So if you want to do searches with synonyms and near misses and that sort of thing. They can also be vectors. So if you've worked with vector data before with AI, generally you run some bit of unstructured data like an image or the text from a PDF or something through a model that is trained to understand that, and you get a whole load of numbers out, which is called a vector embedding. And then you have something you want to compare it to, like another image or a query if you're writing a chatbot. You run that through a similar model or the same model. And then the database's job is to decide which of these streams of vectors are similar to each other. So you can do that as well. And there's also geospatial, and blob data basically means images. So you can store everything in here. Said before, it's got a dynamic schema. I'll run through some of these. There's a bunch of other features. But the key thing for how this is built is the database is built to have all of these things from the ground up. So while everything looks like it's in a single table and you can access it through SQL really, really easily, like it's in a single table, underneath, the storage for each type of data and the way we index and manage it depends on what the data is. So it's a SQL database in that you access things through SQL, but it's what's generally in the class of NoSQL databases. And people are obviously like, oh, hang on, he said SQL and then he said NoSQL. But NoSQL generally means not only SQL rather than anything that isn't SQL. So moving along here, it's open source. So where can you get it? We, as the CrateDB company, provide it in the cloud. You can also put it on Amazon or Azure or whatever yourself if you want to. You can go get Kubernetes and run it elsewhere, or you can run it on the edge. And the edge means things like you might have a Raspberry Pi 3, 4, or 5 in a factory or in your house that's acting as like a home hub or whatever. You might want to put the database on there so you can have some level of local storage and querying, and then have lots and lots of little microprocessor devices pushing data into it, and then maybe have a Grafana or something, and then you've got a whole like open source household system of what's going on in my house and keeping an eye on it. So everything's queried through SQL. So if you used a SQL database before, it'll make sense to you. And we can store all sorts of data. So for this sort of group, we're generally interested in telemetry type data, so sensors and consumption and so forth. But we might also be interested in unstructured input. So you might be taking pictures with your Pi devices and then running them through some sort of model which knows something about them. You know, it's trained to detect birds or whatever. Then you might have a whole load of other images stored in the database in vector format. And you can ask the database, well, you know, this image, which images is it most similar to? When have we seen this sort of bird before, for example? And let's keep going. So generally, you talk to a database through connectors and interfaces. I'm going to focus on mostly the MicroPython connector because I wrote it and it's sort of interest to the group here. But if you were using other things, like you might be running Node-RED on your Raspberry Pi, for example, you can plug it straight into there because CrateDB looks like Postgres. It talks Postgres wire protocol. And what do you build with it? Well, you can build anything you want on top of it. Generally, we're going to show a little bit of visualization, but you could use this to build the other end of a natural language chatbot. So, you could ask it questions about, here's an image of a bird. When did I last see this bird in my garden? The database will have stored all of your previous images of birds that an AI model has classified. And it'll be able to tell you, well, this image looks like these other ones and these are the dates. And then you could run that information through something like a LLM that can generate an English language response and build an entire chatbot. A little bit too much for a session like this, but I will be having a session where we build this sort of thing end to end in future. Then let's move along a little bit. So I said you can install the database in a number of places. So today we're going to look at a cloud installation because it's the easiest thing to immediately connect to, get on the internet and get other devices talking to it. But if you want to run this on your local home network, you could just put it on a Pi yourself. There are there's easy ways and hard ways to do this. So like with any software, you could just go install it on the device. If you've got a higher end Pi, you could run Docker and run a Docker container on it. What I chose to do just for this example was I'd got a Pi 4 kicking around. That's just in a heatsink case. And there is a company called Balena.io. And what they do is they manage software on Raspberry Pi and other devices for you. So CrateDB is in their catalog of software that can be managed. So if you want a CrateDB instance on a Raspberry Pi, you can go to Balena, tell them that you want a CrateDB instance on a Raspberry Pi. And what they do is you install their operating system image on your Raspberry Pi, and they will then push software down to it. So what you see here is I'm logged into that Raspberry Pi when it was last plugged in, and I can see the logs from the database that Balena is running on it. I can see the terminal, I can shell into it and do things, so I can install other stuff. And then I've got a sort of managed database in my home network that is also available to the internet. So Balena allow these to be proxied through to the internet. So if you wanted somewhere outside to see it, you'll see there I've got a public IP address down there. It was 82.4.131. Whatever. And again, Balena is no charge for up to 10 devices. So that's something completely independent of what I do, but it's a tool that I find very useful for this sort of thing. So for getting databases into people's networks on Pis. So how do we talk to CrateDB? Because, databases aren't really that interesting on their own. They're more interesting when we start putting things in and getting things out of them. There's two ways. So there's Postgres port. If you've used Postgres for anything before, that lives on port 5432 and it talks a specific wire protocol or language. CrateDB understands that. So if you have a tool like dbeaver or some of the JetBrains tools that can connect Postgres databases, they'll connect to CrateDB just the same. Similarly, with all of your software, if you're using a Postgres driver for Python in some Pi project and you're writing things to a Postgres somewhere, it's just a case of changing the endpoint and you can go talk to CrateDB. We'll specifically be looking at the HTTP interface, which is simpler for microprocessors. You can just send an HTTP post like you're talking to an API or something and put some SQL in that in the right format, give us some credentials to log in, and we'll run the query against the database. The database will return a JSON document with the response in. So we'll see how that works with small devices. But first off, what I'm going to do is just look at a couple of capabilities of the database so you get an idea for the breadth of projects that you could build with this. I've got some open data from Chicago. So the city of Chicago is very good at providing open data, and it's about different parts of Chicago. And I know there's some US folks on here, but for those not in the US, if you call 311 on a phone, or nowadays you don't call on the phone, you go on the website, but it's usually like dial 311 dot whatever your city is .org, then you can file like a non-emergency request for things like the street light outside has broken, or my neighbor is being really noisy, or why did you not collect my trash this week? So we have some data about that we can look at as well. So what I'm going to do is just slip out of PowerPoint into the real world. And this is a CrateDB instance that I created in the cloud. This is free and it's got about 8 gigs worth of storage. And as long as you log in and use it periodically, it's basically free forever. We'll keep your data in here. What I've got in here is some tables that I already created. So we've got a table that talks about community areas of Chicago. It has some fairly simple fields. It has this interesting one called boundaries, which is a geo shape. So it's a bit of JSON that describes a geographic area. And then we have an object in here that has some other fields. So sort of like a JSON document. And in CrateDB, we can either define some schema for an object, so I knew what this one looks like, or as we'll see later, we can just say, yeah, it's an object, deal with whatever we put in there, and the database will do that and index it for us. We have some other stuff in here as well. So we have a lot of 311 calls, and we have some data we're not actually going to use. Then the best way of demonstrating this sort of stuff really quickly is through a Jupyter Notebook. So a Jupyter Notebook is a way of running Python. Here I'm using Google Colab, which is in the cloud, so you don't need any infrastructure whatsoever. And I've connected myself to that CrateDB instance. So what we'll do is do something you should probably not normally do. And open this up. You'll see here, I'm connected to the database. I've got a connection string. It's got a username and a password, and this is a throwaway database. So if anyone's watching this later, you probably won't be able to connect to it. And there'll be nothing interesting in there. But I'm just connecting to that using something called SQL Alchemy, which is a standard Python framework for talking to databases. So nothing new to learn. So we'll skip over creating tables. But some of the sort of interesting things I wanted to show you with the database to start with were around geospatial. So we have in our schema here, we have this boundaries field. So if we do, what do we want? Name boundaries from community areas. Boundaries is an object, so we need to do details. And then a field called boundaries. This kind of maps reasonably well onto what you'd expect with Python if this was a dictionary. Oops, I can't. Oh no, sorry, it's not in the details object, is it? Look at that. It's in the top level. I was right to start with. Okay, so let's do that. Select name and boundaries from community areas. And you'll see here I've got all of the community areas of Chicago and the coordinates that make up their boundaries. So the obvious thing we want to do with that, for example, would be to build a map with them. So I've got a framework called Leaflet here, which we won't go into the details of, but it allows me to plot things on a map. And the important thing here is I can get geospatial data out of the database, and then I can put it on the map by just adding what's called a GeoJSON layer. So the data is already in that format in the database. It's very easy to work with. So if I do run this query, what we'll see when it finishes, and this is a nice slow environment because it's a shared collab environment, is we've got a map of Chicago here, and you can see all of the outlines of the community areas, and the color coding is relative to the population. So it's basically a population density map. Because up here in my my query, I was selecting, I want the population from the details object that we put in the database, and I want the geo boundaries. And I just have a little function here that determines how many people live there and colors the thing differently. So that's some very basic geospatial stuff. Something that is more interesting, and I'll just go ahead and run this and then talk about how it works, is you might want to build something that is more interactive and does searches based on the map. So if you've got a fleet of devices or something out there that are writing data into the database, so you've got like weather stations or whatever, then you might want to draw a polygon on the database, on the map or something, and say, well, what's going on in here? What we're going to do here is if I move this marker here, you'll see another marker appears. And when I click it, there's some data here. So what we're showing here is I'm actually showing what the nearest library to the red marker is. And how that works is, again, we've got a fairly simple but slightly longer SQL query. We're just selecting details about libraries, which is another table that I created. But what we're doing is asking the database to find the distance between the lat long of the library in the database and the position on the map, and then order them by that. So we can do geo queries. That's the basic thing I'd like you to take away from this. We can also do more complicated geo queries. So imagine I was taking a trip, and here's the sort of Google Maps line for my trip. And I'm going from, in this case, downtown Chicago over here to out to O'Hare Airport, which is like the big airport in Chicago. And what you might want to know is we've got data about community areas. So you might want to know, well, which community areas, which neighborhoods does this trip pass through? Or if you are building something with like a vehicle, yeah, it might be which toll areas has my vehicle driven through, or whatever your movable object is doing. So what we can do here is with, again, standard SQL, write a really simple query that says, I want the name and the boundaries of all the community areas whose boundaries intersect with my trip. So which areas am I passing through? And when I run that, you'll see that we've gone through 10 areas on the way. And we got some background noise. Could you mute, Isaiah? Thanks. Thank you. We've gone through 10 areas on the way, and we can see what the boundaries of those are. So knowing that, we can start to build up more complicated queries. And again, if you're working with sensors, a lot of the interest in sensors is combining it with other data. So, you know, geospatial, other streams of data, things in JSON documents. So if, for example, we know which community areas we're going through with the data we've got, and we know that people phone 311 and complain about stuff, and we know which community area they complain about stuff in, we can then write a reasonably complicated SQL query here, but one nevertheless that says, for each of those areas we're passing through, tell me about all the problems on the 311 table that are currently open tickets and relate to road things. They talk about potholes or streetlights or sign repairs. And you can see here we get now a count of the how many issues there are. So you could say this is sort of a way of looking at the quality of the road in the area. And then using what we did earlier to put things on a map and have different colors, we can now say, okay, so here's my trip and here's the community areas it passes through. And now they're colored by the number of open issues to do with roads. So, yeah, this trip looks like we're going to set off in downtown Chicago. The roads are pretty good. And then whatever that next neighborhood is, that's pretty bad. And then, yeah, progressively not great. And then it gets better as we go out to the airport. So the point of an analytics database like CrateDB is to be able to answer these sorts of queries of, lots of data over time, where the value of the answer is basically based on aggregation or summaries of the value, not an individual value itself. So you wouldn't use a product like this for example, keeping track of how much money you got in the bank at a given time because it doesn't have transactions. You don't need it for an analytics type database, but you might use it for things like, say I've got sensors in all of my rooms at home, what is the trend over time of those? And then you might be able to combine that with some sort of AI model and predict things. So you might also compare it to, for example, the outside weather and then be able to predict what your utility bills might look like based on the weather, if that's a big factor in whether you do put the heating on or so on. So this is a not particularly related to Raspberry Pi stuff, but what I wanted to do was just sort of give you a flavor of what you can build with this. Then what I'm going to do is go back to here and look at something that's very Raspberry Pi related. So, one of the most common projects that people that get a Pico or other microcontrollers might want to do is use it to gather some sort of input from a sensor and send it to something in the cloud or on your local network or whatever that acts as a store for all of that data and then either can summarize it and display it back on a little display or can take some sort of action when some events triggered, like when it's too hot for 20 minutes, turn the air conditioner on, that sort of thing. So we do a lot of this sort of talking to things from microcontrollers. And the example I'm going to show here today is the microcontroller talks directly to the database. If you're a production solutions architect, you might say, don't do that. The microcontroller should talk to like a streaming solution, and then you can route the data to multiple places and so forth. And absolutely, yes, you can and you should. But what I wanted to do was show a really stripped down example of how you, in a hobbyist situation, could take a powerful open source database that we have in production with customers with massive amounts of data scale and use that either on your Raspberry Pi 345 locally or in the cloud to get some value from things that you're doing at home. And for that, talking to the database directly from microcontroller is totally acceptable. So back to the real world of actually doing things. So over here in my database, I am going to create a table and we're going to send some sensor readings into the database and look at how that works in MicroPython. So what I need to do first is we'll just do this and then we'll look at what it actually did. So for those of you who aren't too familiar with SQL, you insert and query things with SQL. You also change the structure of the database with SQL. So I'm creating a table here And the result of that is okay. And then up here, if I refresh this, we should have a new table in here called sensor readings. So what did we do? Well, we created a new table called sensor readings, and we're going to chuck sensor readings in there from Pico Ws. What we're saying is each reading comprises of a sensor ID, so something that identifies the device that sent it. So we know, for example, which bedroom it's in or which zone of the house it's in. If we're going to put that on a dashboard, then we are going to make the assumption that we don't want to manage time on these little devices. So Picos, etc., don't have a real-time clock built into them. So we're going to let the database be the arbiter of time here. So we're saying, okay, generate a value for the current timestamp every time someone puts something into the sensor readings table. This kind of means that you get the time when it hits the database for the event, not the time when the event happened. But in this situation, there's going to be very little difference between us recording temperature, sending an HTTP post to the database, and the database saving it. If we were using like streaming data architecture where we record the temperature and like sometime later it bounces its way around a complicated network to get to a database, we'd want that original time when the event happened, not the time when we happen to store it in the database. And for that, you'd probably want a real-time clock. And what I'm also doing is to help with analytics, I'm having the database also generate a timestamp for the month that this event happened. So we can then easily and quickly aggregate things and draw a graph of, say, give me all of August and September's temperature readings. We don't have to go through all of these timestamps and work out what month they were in. We've got something here that has done that for us. And then the only value that we're actually going to store in the table is a temperature for now. And we're going to say that we want this table to be dynamic, which means if we store something else in it, the schema will grow. So we'll see what that means. So right now we have nothing in there. So if I do select star from sensor readings like this, you can expect to see basically a blank table with 4 columns. So sensor ID, timestamp, and so on. If we just show what a quick insert will look like, I've cheated here. I'm choosing to use the IP address of the sensors as their IDs. So we'll just put a pretend in there and say it's 12.2 degrees. Oops. And I think I have to not have that selected. There we go. There we go. That's better. So I've inserted a value into there. So if we then do select star from sensor readings, then what you see happens is here's the 2 values we put in, 12.2, a temperature, and a sensor ID. And then the database has created 2 other values for us. So this is the timestamp of when we did it, so 7:39 p.m. my time. And then you'll notice here the month one is the timestamp of the 1st second of the 1st of January. So it's generated that for us. If we want to aggregate and find all the January ones, we can do that very, very easily. It's also important if you're running like continuous data gathering like this to bucket things like this so that you can eventually delete them easily, because database space isn't finite. So it is finite. We're eventually going to run out of space. So you're going to want to delete old things. So having them easily addressable by a unit of time that you think is appropriate, so a month or year or week or even day, makes a lot of sense. Right, so that's a bit of setup. We've got a database with a reading in it. How do we get stuff in there from, that's going to come into focus eventually. There we go. I've got some devices here. These are all Picos. This one's got a Pico in the back. And what we've got here is a Pico with a fairly standard DHT18 temperature sensor on it. That does temperature and humidity. Then we've got a light and a sound sensor. And these 2 here are connected to what are called Grove shields. So broadly, Grove is a standard that relates to these cables and these plugs that lets you connect sensors or other things, like it could be a display or a a horn or a motor or a relay to devices like a Pico very easily in a plug and play way without doing any soldering. So there's this is absolutely a standard. I happen to get all of this Grove stuff through a kit here from Seed Studio, which is a nice way of getting started with this. So if you want to play with specifically Picos and you don't want to deal with soldering all of these devices to them or crocodile clipping them or whatever, then Grove's great for that. So we've got some devices with Grove. We're going to start with this one here. There's obviously not much visual to looking at this device because it's just got a temperature humidity on it, but I wanted to have it on the camera so you can see what happens when I, for example, plug it in here. Yep, there we go. That had briefly frozen. And I've briefly disappeared. I'm back, I think. And can you hear me, Richard? That's what happens when you have a Macintosh and you plug something into something that's got a lot of things plugged into it. It generally gets upset. So we've got a Pico, and what we're going to do is quickly just connect to it. So Stuart's going to talk a bit about how the Picos work later, so I'm going to make some assumptions here. We're running Thonny here, which is an IDE for editing either C or Python code on little devices like the Pico. And we've got some MicroPython code here. And then down here, we've got a REPL actually running on the little device. So I can do, actual type in Python commands and they're going to work. I can do 1 + 3 and we should get 4 back. So I could interactively build things up on here, but I can also run code on here and see the results. So how are we going to get data from that sensor that's attached to this device into CrateDB? Well, what we're going to do is use a standard library for the sensor. And this is a microcontroller, so it's not a full Raspberry Pi with an operating system and agents to do things for us. So we're going to talk to a cloud database. So we actually need to connect to a Wi-Fi connection and provide a SSID and a password to a Wi-Fi network that I've got here. Wait around until we're connected to that. And then once we're connected to that, what we're going to do is basically sit in a loop forever that's going to read the temperature from the library for the sensor. It'll give us a temperature and a humidity back. And then we're going to create a standard SQL statement that says, okay, I want to insert that temperature into the table called sensor readings. And then if you're familiar with regular Python or MicroPython, there's a library called requests for dealing with HTTP APIs. We're just going to post that SQL statement into the URL for our cloud database, or it could be a database running on your local network. And in that case, it would just be the IP address of it. And we're going to log in by providing some basic authentication and send the statement. And what's going to happen is database is going to run the statement, do the thing, and if all goes well and we don't get any errors, it'll tell us how many rows were affected. And hopefully that's 1. Then we're going to go to sleep for 10 seconds and just do this forever. So the most basic way of getting data in is to do an HTTP post. And that means that the types of devices you can talk to CrateDB from, there's huge because the requirements are very, very, very low. There's no extra software or libraries needed here. We're just using the request library to post things in. So let's go ahead and run that and see what happens. So the output down here says it's read a temperature and humidity and it's inserted it into CrateDB. There's actually nothing to see here because there's no LEDs or anything that tells us what's going on. So we're reliant on the REPL here. So after 10 seconds, it's woken up and done it again. And guess what? The temperature's not really changed. So if I go back here and run this again, what we should see now is we're starting to get values. And let's do put them into some sort of order. So order by timestamp. descending, so the latest one first. What you see is we're starting to get those values, and I've got just a temperature, and my table's got just a temperature in it. And all's good. They're coming in through the HTTP posts, so nice and simple. Now, I said earlier that the schema in CrateDB is dynamic, and that's kind of semi-special for relational databases, because normally, if we wanted to go ahead and store this humidity value that we've also got, we'd have to go back to the database, run something called an alter table statement, and say, I want to alter this table and give it another column for humidity. And then we'd have to come here and go, okay, I want to put, let's say we called the column humidity, and I think it's called humid in the code, add another thing here. We'd have to modify this. And then in the database, we'd also have to tell it what type of data to expect in the humidity column. So what you would normally expect if I run this with a lot of databases is it's just going to fail. And what's not happened is it's not failed. So it's succeeded, but has it done anything interesting? So now we've got temperature and humidity. We're telling CrateDB about them as well. So when we run this, what you'll see is, yes, the database has extended the schema. We've got this extra column, humidity. It's got values in, and then obviously values that were created before we did this, we can't make up humidity values for those, right? So they're still null. But we've got a database now that if you're dealing with something that's quite flexible or changing, or different sensors have different parameters, or you upgrade your sensors over time, you don't have to do too much about upgrading your database. Because it's an analytics database, it's pretty forgiving of this sort of thing, because it wants you to put data in there, and it's also indexing this new column automatically, which will make it faster query. So our first sort of Pico demo, we've gone from sending simple HTTP requests, so there's like 0 external dependencies, to showing a bit of flexibility of schema. So what I'm going to do now is play a bit of a switcheroo on the Picos. And here's another one that we prepared earlier. So this one has got 2 sensors on it. And I can see that Zoom is going to think this is a camera every time I do this and turn my camera off. So hopefully I'm back with you again. So this one's got 2 sensors on it. Let's just pull them apart a little bit. There's a light sensor and a noise sensor there. So they're not temperature and humidity sensors. And let's just connect to this guy. So we've got a REPL for that as well. And what we've got for that is some slightly different code. Oops, not that one though. What we've got for that is the light noise sensor code here. So let's pull this down. So for this, we're using, we're just basically reading from ADC as the analog digital converter in MicroPython. So this is all MicroPython stuff. We're just reading from the analog digital converters at different pins on the Pico. Those will give us values for light and sound, and we'll look at how that works. And then what I'm doing this time is I'm not making a HTTP request with the request library. I've imported something called CrateDB. So CrateDB has a driver for MicroPython, which I wrote. I say that because I can explain how it works. And what it does is it abstracts away some of the details of that HTTP request and the mechanisms of authentication for you, and makes things a little bit easier to deal with and more Python friendly. So for example, now rather than making an HTTP request, we're just going to set up a new instance of the CrateDB class and tell it where our database lives. We're going to connect to the Wi-Fi like we did before, and then we're going to read each of those sensors. So the way that works is it's an analog digital converter. So we're just going to read a unsigned 16 number from each of those. And here, instead of doing an HTTP post, we've now got a method in our driver called execute. And we're going to say, okay, let's insert into the sensor readings table a sensor ID, a light, and a sound, and pass those values in. And when I run this, again, what we should see is we've got, number one, a little bit of an easier way of coding this. We're not dealing with the low-level interface so much. And what we'll see is we've got some values down the bottom there, and I'm holding my finger over the light sensor to get a bit of a darker value, make it do something. The sound one is pretty sensitive to when it actually fires. There we go. So we created some sound. All of those have gone into the database. Again, when I run these, what we'll find now is values from this sensor that has an IP address ending in 20. They don't have temperature and humidity, but that's okay. They have light and sound, and we've again extended the table schema to cope with this. So I'm just going to stop that. And then we have a third and slightly more complicated device. So this one here is a Pimeroni Pico Enviro Plus. That's quite hard to say. And what it is it's got some sensors built into it for different things. It's got like a gas sensor, light, sound, temperature, humidity, and so on. You bring your own Pico W to go in the back, and well, or just a Pico if you want, because it's got a display on as well. So you could just gather values locally and output things. What we're going to do is gather values with this Pico W using the extra sensors on here and send them to the database and look at how that works. So very, very quickly, and you'll probably lose me on the camera again while I plug this in. There it goes. So let's come back, turn the video on. There we go, we're back. So another thing that I have learned from doing these demonstrations and working with these devices is blue tack is a really good friend. So this, you can't see it, but if I blue tack it to the desk, it won't roll over. So this you can see, cell down, there we go, has got a little screen on it. And every so often, it's going to send data to CrateDB and report that it did that. And it's just going to sit in a loop and do that. So let's have a look at the code for this. So I've got the Enviro Plus folder here. All of this code's on GitHub, by the way, and I'll share it afterwards because these are fairly common devices. So if you want to play around with them. This one's more complicated and it uses a lot of Pimeroni demo code to do with their device having more sensors and a screen, but we'll skip over the majority of that. So again, we're going to use the CrateDB driver. We're setting up talking to CrateDB. We have to talk to the Wi-Fi. And what we're going to do this time is skip over a lot of Pimeroni boilerplate about drawing on the screen. We're going to read all of their different sensors with code that they provided. So they have a different sort of temperature sensor, and they have a different sort of light sensor and a noise sensor and so on. At the end of the day, what we're going to do is, again, standard insert into sensor reading SQL thing. And what we're going to do is have different sorts of sensor. And then the interesting thing with this one that we've done differently is others here is a Python dictionary. So it has pressure and gas values in it. And what happens when we insert that into the database is we should be able to see over here that values that are coming from that Pico Enviro, they've got a temperature and a humidity, they've got a light and a sound. These are generally more accurate because they're better quality sensors than the other ones. But there's this others column that the database has realized needs to be an object because we give it a Python dictionary. So the database has gone, oh, they gave me something that looks like an object. I'll make an object. And inside that are other values from those sensors. And if you've got data that gets like arbitrarily complicated, we could, for example, I just uncomment these lines and put a comma there to make that a valued dictionary. We can have a dictionary that has a nested dictionary inside it. And I'm not going to change anything else in the code here that talks to the database. I'll just save that. And then let's connect to our device here and let's start running that code on here. And what you'll see when it writes things to the database is that those values now, so the latest one here, the object value here has gas and pressure, but it also now has a sub-object called location. And we've put the information about the location of the device in there. Is that a good idea, really? No, you wouldn't put that sort of information in there because it ends up in every single record and it's just repeating stuff that doesn't add any value. But if you've got something complicated, like your device was calling an API, or I have one of those flight tracking, I think it's back here somewhere, flight tracking sticks that people use with Pis a lot, they generate a ton of data that has all sorts of different shapes. So if you wanted to put that in a database and try and make sense of it, you could use CrateDB for that. And it's just as easy as make up a Python dictionary that looks like it in MicroPython, shove it in the database in an insert statement, and then the database will figure out what it's going to do with it, and you can start querying it. So, we could basically ask it questions like,
Sure,
something
Simon,
like,
we're running out of time.
that's okay. I will, so we could ask it specifically, I only want the gas field, for example, and then we can start doing aggregations over that. So that is that's a quick tour of the database itself. What I really quickly was going to show you off the back of this was how I created that MicroPython package. So a MicroPython package is something that you can put onto a Pico and use, and there's a way of distributing it. You need some source code files, a package JSON, if you've got more than one file that you want to push onto the Picos or other MicroPython devices, or if you've got dependencies on other libraries. So some libraries depend on other things. And you put those in GitHub. You have a package.json file that looks a bit like this. It describes what your library looks like. So when you install the CrateDB library, you get a file called cratedb.py, and that's where it comes from. And it depends on something called base64. And base64 comes from the MicroPython lib library, which is the tooling understands how to install that. And then if you want to install things on there, you basically build a library. My library has a class. So once you have installed it, you can import that CrateDB class and work with its methods. And how to install it, you can either write a little program on the Pico that connects to the network and uses MIP, which is like pip on regular Python, to install it. Or probably a better way, you can use the MP remote command on your regular Pi or your desktop computer and connect the Pico to it and have it install that. That will then install a couple of things on there. So there's a folder in the Pico that becomes lib, and anything in there, MicroPython programs can just import, and it puts your files in there along with their dependencies. So that was really all I've got. My last thing I'll skip over to was we've got some other examples of projects, but really, if you want to learn anything more about CrateDB, I built a free course online, so I would recommend you go take it.
Excellent. There are some questions in the chat. Maybe you can answer those throughout the next talk. We're just
Yeah,
running
I'll
short
be
on
here,
time.
so I
We do
will.
have a hard stop here at 9, so we need to make sure all that works.
Okay. With that
So
said,
why
I'll
don't we
hand
do
over
that?
to Stuart.
Yeah, so if people have questions, they can put them into the chat, and Simon can answer those. And maybe we'll come back at the end if there's still some time, and do some live questions for Simon as well. Thanks, Simon. That was really interesting. It's obviously a
Thank you.
very flexible database. I've just about rewriting some of my projects. So it's just
Exactly.
make things a bit
Thank,
easier.